Math Humans. We're going to do 4.2 today. We're going to be talking about exponential growth. So our objectives are that we're going to manage exponential growth and we're going to compare it to linear growth. So we're actually going to start with our linear growth. So linear growth was what we did yesterday, and here was our model. The population in terms of time is equal to the initial population plus D was the common difference. Oh, that's a long word. And then T obviously is going to be time. And the graph for linear growth might look something like that, where this is your P of 0. The y-intercept is going to be your initial population. And then time is going to be our x-axis because we're not allowed to change time. So then what we're going to talk about, the next item, is linear growth, exponential growth. We just did that. So for exponential growth, we have the same variables, but the equation looks a little bit different. The biggest thing to notice is, notice that time is in the exponent position. So the variable now is in the exponent position. So P sub 0 is still the initial population. Okay. R is going to be the rate of change. So rate of change, and it could be growth or decay. Okay. If it's positive, it's going to be growth, and if it's negative, it's going to be decay. And the graph for exponential looks very different. So it looks like this. And we've talked about this a little bit in the past, but linear growth could be maybe your big ticket items, like a car, it could be a boat, or it could be a house. And so linear growth is something that's going to change by the same amount each year. Exponential growth could be, it could model a population. So can linear growth, because we did those yesterday. But the big thing that we think about when we think about exponential growth is credit card debt, because your debt grows exponentially fast. And so those are kind of the differences between the two graphs. You can see that this one is growing very slow, and this one is growing very fast. Okay? So now we're going to start with an example, and then we'll use the model that we're talking about today for exponential growth. All right, the first example says a city is growing at an exponential rate of 1.6% per year. The initial population is 125,000. I'm going to underline the important things. The first thing that we're going to do is write the exponential model, because we always have to write the model first. And then we're going to calculate the city's population in 25 years. So my model, P of T, is going to equal the initial population, or the initial price, or whatever, times 1 plus or minus R raised to the T. So our initial population was 125,000, so I'm going to write 125, and then 1. It says that we are growing, so that means this is going to be plus. And when we write our R is always going to be in decimal form. And remember, if it's a percent, that means I'm going to take that value and divide by 100. So this is going to be 0.016 and then raised to the T. And then this is going to be my exponential model. Okay. So now I want to put this into my calculator. So I'm going to do 125, and then this is 1.016 raised to the T. There's my model. And now I want to predict what happens in 25 years. So P of 25 is going to be the 125 times the 1.016 raised to the 25. So if I get out my handy-dandy calculator and show you that calculation, so I'm going to do 125 and then times. I don't have to put in the times symbol. 1.016, and then I'm going to raise it to 25, right? And so then there's my number. Whew. Now remember, in this particular problem, we're talking about a population of people, so that means that even though I get a decimal, I have to round to a whole number. So I'm going to write that my population is equal to 185,889. I rounded up. So remember, when we're talking about people or bugs or things, you can't have a piece of it, and so that means that you need to round either up or you can round down. But you can't have a decimal of a person, a decimal of a bug, or a decimal of a thing. And then we want to report our answer well, and we want to include the units. And the units on this is, what does this number represent? And in this case, it's going to be people. And technically, it would be people in our city, but we're good to go. Okay, so now let's do another example. In this one, our population is declining. So St. Louis, Missouri has declined in population at a rate of 1.6% per year, so I'm going to underline those two important things, over the last 60 years. The population in 1950 was 857,000, and I want to write the model, which is task number 1, and then I'm going to calculate the population in 2014. So the first thing that I'm going to do is I'm going to write down the generic equation, because it helps to substitute in numbers when I know what I'm substituting in. So here is my P of T. My initial population in 1950, which is the year that they gave us, is 857. And then it's declining, which means my rate is going to be negative, so it's going to be 1 minus 0.016 raised to the t. And if I clean that up a little bit, it's going to be 857, and then 1 minus 0.016 is 0.984 raised to the t. So this is our model. The second thing that we want to do is calculate the population in 2014, so we have to figure out how many years have gone by. So 2014 minus the year that they gave us, 1950, is going to be 64 years. So when I predict, I want to do P of 64, so it's going to be the 857 times the 0.984 raised to the 64. And we just talked about how to do that in your calculator. And when you do that math, you're going to get 305258.05. We can't have 0.05 of a human, so I'm going to say that P of 64 is 305258. I'm going to round down to the next whole number, and then I'm going to include my units, which are people. Okay? So the next problem is going to be a slight variation on what we've done for these two. Okay? So the next one says, according to a news forecast, the population of Puerto Rico is in decline. Okay, so I'm going to underline decline because that means negative. The population in 2010 was 3.9 million, and the prediction for the year 2050 is 3.6, almost 3.7 million. So in this one, we're actually looking for R. So R is the thing that we're going to find. So I'm going to write down what I know. I know that my initial population is 3978123, and I know that from 2010 to 2050 is 40 years. So my time is going to equal 40 years. And in 40 years, P of 40 is going to equal the 3697123. So now I'm going to write my equation. So P of t is equal to P sub 0 times 1 plus R to the t. And R this time is what we're looking to solve. So they gave me an ending number, so I'm going to set up my equation as 3697123. is equal to my initial population, 3,978,123, times 1 plus r, and this number happened when we had 40 years, so I'm going to put a 40 up there. The goal is to solve for r, so that means that I need to isolate this part of the equation. So now I'm going to divide both sides of the equation by that number. Okay, so 3,978,123. And just to make it easier on my calculator, I'm not going to enter those zeros. Okay. Now, it will also tell you this, because we are raising numbers to an exponent, I will tell you not to do this yet. Okay, so I'm going to write 1 plus r to the 40 is equal to 3697 over 3978. The goal is to solve for r, so since this whole thing is raised to a power, I have to raise both sides to the reciprocal, or the opposite. So 1 over 40 is the opposite of 40 over 1. So I'm going to raise this to the 1 over 40. Okay? And I'm not going to push buttons on my calculator because these values are so big, it will create a lot of error. So I'm actually not going to use my calculator until the very end of the problem. So now I have 1 plus r is equal to the 3697 divided by the 3978 raised to the 1 over 40. Now I need to get rid of the 1, so I'm going to subtract 1. And now I have r all by itself. So now I'm going to do this in my calculator. So I'll show you how I'm going to do it in my calculator. So I'm going to do, in parentheses, 3697 divided by 3978. I'm going to raise it to the 1 divided by 40. Now, if you have one of the older calculators, and I'm going to zoom in a little bit so you can see that better. When you do your raise it to a power, if it doesn't come up like this, if you just get a caret and it stays like that, then you need to do parentheses 1 divided by 40 close. So if you have some of the little old black calculators or some of the older yellow calculators from the school, if your exponent doesn't go up top, this is what you need to do to make sure that it does that math. And then I'm going to go subtract 1. And so if you'll notice, this is everything that we had entered. So now I can push buttons, and there's my answer. So I'm going to record my answer. R is a negative point. The negative is good because back in the original part of the equation, it said that it was in a decline. Zoom back out. So I get a negative 0.0018, okay? And so this would be my R. And so if I want to put this in percent form, remember that I would divide by 100. And so this is, R is going to equal 0.18%. Okay, I'm okay if you leave it like this. This is probably just as easy, but it is a very small percentage. And then this would be my annual decrease. Alrighty, I will just re-caution you, don't push buttons because we're raising these to such big or small, super small exponents. Don't push buttons on your calculator until the very end of the problem. All right, my dears, that is it for today. I will see you soon.